continuing with our penny example, we now want to be able to answer all the questions on this page. All right, so let's remind ourselves real quick. We came up with the center and the spread here at the bottom of this last page. Now remember, we need to make a note. I guess I'll have to put it here. So note, use these values in stat calculator normal, right? In the stat calculator normal section, we have to use these values. This one will be the mean. This will be the standard deviation. That's the way that works. Right? Because the mean is the center and the standard deviation is a spread. And this is a standard deviation. The standard error is the standard deviation of the sampling distribution, right? It's of the X bar distribution. All right, so let's get to here. So we have here, and it wants us again to find a probability. See the P parentheses. So if we use our technology table right here, if we want to find a probability, we'll put the mean and the standard error right here, and then we're going to put the X bar that's given here, and it will find the area for us. The area is the probability. Area and probability are one and the same under a normal curve. Now, I notice when I look at this problem that it's a between problem because it has two numbers given. I'm actually going to try to adjust my paper so you can see both. One second. There, I just wanted to make it so you could see both things at the same time. It'd just be easier. So let me show you again. Stat, calculators, normal. There's the normal calculator. And for the mean, we're going to use the value from the previous page, right, which was 12.2. So 12.2 years is going to go in as the mean. And the standard error is going to be 1.5653. That's the standard deviation, which is the standard error. All right, so we put those values in. And then we want it to be between, because I can see there's two numbers there. So I'm going to click between, and I'll put 10 here and 14 here, and I'll press enter. Oh, and I should have mentioned, but I'll be doing this all in StatCrunch. At the very end, I will show how to do it in a calculator. So let's see here. We need to shade. Right, that's our zone. Here's 10, here's 14. So we're looking for that area in between. So I will write it down. Probability that 10 is less than or equal to X bar, which is less than or equal to 14. I know it says X, but it's not really an X in this case, right? It's an X bar. It's right there. Is 0.790. So 497, that 7 would round up that 49. Oops, sorry, I didn't mean to do that. 10, 14. There we go. That 7 would round up that 9, and that 9 would round up that 4. So it's actually 7950. That's the result. And it doesn't have units because it's a probability. Probability doesn't have units. All right, now, there's a 20% chance the mean age of random pennies will be at or below. Okay, so because this is below, we're going to be doing a left tail. We're going to be doing a less than. If it was above, I'll make a note. If it was above, you would be doing a greater than sign, just on a side note. Okay, so we're going to switch to a standard. And notice the mean and the standard deviation stay because they are the values that they are. But the 20% chance that it's below, at or below. So we're looking for the mean age. We know the probability. We know it's 0.20. So we know our area. We're trying to find the X bar. We know the area is 0.20. So we're going to put 0.20 over here on the right. There we have it, 10.88. Well, we could round because it says to round to 1 decimal place up here. So we'll say 10.9. All right, so let's shade. So we have 20% of the curve is shaded. This is the part that's given, right? You know that that's 20%, and you're looking for this value. At or below what value? So when I write this out, I'll say x bar less than or equal to 10.9, and I'm going to leave space because there's actually a unit there, equals 0.20. So this is the answer, but it has a unit to it. You'll notice I wrote give units. Okay, so what's the unit? Well, because this was age, this was the age of the pennies in years. So that's the unit. It's the unit for the data set. All right, now you have 40 pennies in your car. Would it be unusual if they had a mean age greater than 16 years? Explain using probability. All right. First of all, unusual. Unusual is a specific definition that we've run into several times. And for right now, our definition is what it has been since chapter 3, which is less than 5%, which is 0.05. That's our threshold for unusual. All right, so you'll notice we have an age. We have an x bar. It's right here. It's 16 years. So we have an x bar given. And we're looking for, would it be unusual to be greater than that, above that? Okay, well, again, let's look here. I know my x bar is 16 years. I mean, it has units on it for starters, so it's this one. So I know that that's 16, and I want to go greater than, and it will give me the probability. It'll give me the percent, right? And I want to be able to compare that percent to 0.05. So I'm going to switch to a greater than. I'm going to change this to 16, and there we can see. It's a very small tail. But this was 16. That was the known part. So the probability that x bar is greater than 16 is equal to 0.0076. So there's the probability. Now we want to make sure we answer the question. Would it be unusual? And the answer is yes, that would be unusual. So don't forget to answer that. I can't tell you, people lose points all the time because they forget to answer. Yes, x bar greater than 16 would be unusual. Oops, I just spelled that wrong. Unusual. Because the probability of 0.0076 is less than 0.05. You don't have to, by the way, say the x bar greater than 16. You can just say this result would be unusual if you don't want to get specific about it. All right, so now let's answer the question of, suppose you actually did this. Suppose you had 40 pennies in your car, right? Would it be unusual? And you have it, and it is unusual, but you have it. You have the average age of those 40 pennies in your car is greater than 16 years. So what are some possible conclusions you could draw? All right, so there's 3 broad categories. You could have a biased sample. So maybe you're a penny collector. Maybe you're a hoarder. Maybe you're driving around in your grandparents' car and they just haven't cleaned it out since 1978. I don't know, right? So there's lots of different reasons. So you're just trying to think of one. Maybe you are a penny collector. So your sample is biased. Right. And there's usually tons of examples of this, right? Basically, you're trying to figure out a way that you've ruined your sample for yourself, right? Somehow you've left off this group, this type of group, or somehow you have too many penny collectors in your group, or somehow you have too many of this or that, right? That's all biased sample. Now, the other possibility well, I shouldn't say there's two other possibilities. Another possibility is it just happened. You know, weird things happen all the time, right? So, weirdly, it's not because your sample was biased. It just happened by random chance. Now, the probability of that random chance, the probability of this fluke, right, this weird thing happening by random chance, is 0.0076. Right, that's what you were finding in letter I. In letter I, you're saying, assume this is random and not biased, then what's the chances of getting this weird result? And the answer is 0.0076. And yes, it's a weird result. That's what we answered. So, but it could happen, right? It's not zero, right? And then the last bit is that everything we did on all of these pages, for both the last page and this page, assumed certain values. There were parameters that were assumed. And maybe they were wrong. So maybe we built everything on a faulty foundation. So if you look back a page or two, we built everything on 12.2 and 9.9. It's back up here actually at the start. See these two values right here? Right? The mu equals 12.2, the sigma equals 9.9. Right? Those are parameters. Those are population parameters. They're values about the population that we assume to be true because of magic, right? So maybe we were wrong. Maybe they're not the value that Alana found on the US Mint's website. It could happen, right? So the parameters of mu equals 12.2 years and the sigma equals 9.9 years, maybe they're wrong. Maybe they were never right to begin with. Maybe they were wrong or were correct at some point, but have changed over time, or maybe they were always wrong. Who knows, right? But one way or another, it's wrong. All right, so I'm going to go show this how to do the calculations above with the TI-84. So if you're not watching a TI-84 or using a TI-84, you can just skip ahead to the next video. All right, so back here with this problem with letter G. So let me bring up the calculator one second. Okay, so if we want to find the probability, we would use normal CDF. All right, so for the first one, we would use normal CDF. So second distribution, normal CDF, you would say 10, and then you would say 14. And then we'd use the mean, which was 12.2, but maybe that's a faulty assumption, but that's what we would use. Oops, sorry. I'm trying to type and it's not liking me. 0.2. And then sigma is not 9.9, it's 1.5653. There we go. And we paste those values in, and there we have it. Same answer. Now letter H is a little different because letter H, we know the area is 0.20, so we have to use inverse norm. So we'd use inverse norm. Luckily, this is another left-tailed one, so it's just 0.2, and again, we have to type in those values. So 12.2 and 1.5653, and it is left, so we can just paste it in. The old calculator would work the same way. It just wouldn't have the left part. All right, and then down here for this one, we want to go greater than 16. So we actually want to do normal CDF again because we want the probability. So we would say 16 is on the left-hand edge of what we shaded. 1E, which is above your comma, 99 is standing for infinity. And then we would say 12.2 and 1.5653. Enter. And there you have it.